invite our speaker up today, Mike Tritt. So, welcome, Mike. So,
thank you, Drew.
Mike has more than 30 years of experience in the engineering and construction industry and has been active in strategic pursuits in the oil, gas, underground storage, and power sectors of North America, Europe, and Asia. He is president of Lane Power and Energy Solutions since 2017. He was previously senior vice president of the energy division from 2005 to 2017. His power generation projects include wasted energy, natural gas, biomass, compressed air, energy storage, and geothermal. He has worked on several national security-related projects and has held a top secret security clearance with the Department of Defense. So he's an influential thought leader on oil, gas, and hydrogen strategic storage, and he has been appointed to the National Petroleum Council by the Secretary of Energy. He's active in the business executives for national security and the co-chair of their energy committee, the Atlantic Council, and the Solution Mining Research Institute. Mike has also been inducted into the Domal, the fraternal organization of the heavy civil and underground construction industry, the most prestigious organization of its kind. He's earned his civil engineering degree from Lehigh University and is a graduate from the Wharton Management Program at the University of Pennsylvania. So we're very pleased and happy to have Michael here today. So if you join me in just welcoming Michael to the stage.
Thank you, Drew. Yep, beautiful. Just this button right here.
Yeah, I'll get that turned off. It's random. So, okay.
All right. Well, hey, thank you very much, Drew, and thank you for the invitation to come speak today. I appreciate it. Hopefully, make this interesting for you. My name is Michael Tritt, as Drew said, I'm president of Lane Power and Energy Solutions. So we are a specialty engineering niche EPC construction business. We do two things. We do hard rock caverns and we do salt caverns. Our team experience. We've done 13.5 million barrels of storage in 9 caverns, most of those for LPG, but also for crude. We've delivered the only hard rock caverns constructed in the U.S. in the past 35 years. Oh, there we go. I don't have to speak as loud now. We've reactivated, actually, you know what, I always ask this question before I start, and I apologize for jumping into it, but how many people here have worked with caverns or around caverns or really have any kind of knowledge of them? Okay, good, we got a couple people in the audience, great. And so I'm gonna make this very interactive. So at any point in time, raise your hand, ask a question, just anything curious, let me know, and we'll stop and answer it. So we've reactivated abandoned caverns, and we've also converted a 73 million barrel hard rock salt mine to the first strategic petroleum reserve site in Weeks Island, down in Louisiana. In salt caverns, we've done 100 plus, we've lost track, salt cavern projects, 25 leach plants, and we designed and constructed the last cavern that the last hydrogen cavern that was constructed, and that was for Air Liquide down in Spindletop, Texas. I'll get this in a little further, but there are only 6 of them in the world, so there are not that many. On our national energy security, we've worked, my partner, who's a little bit older than I am, we call him the godfather of caverns, Tim Reichwein. He started his career out designing and building the Strategic Petroleum Reserve, and we've been doing work with them ever since. Most recently, our national security work is related to the waste isolation pilot plant out in Carlsbad, New Mexico. That's the only deep geologic nuclear waste repository in the United States. So we're doing consulting work on there for storing that, and that's in a hard rock mine down 2,000 feet into a bedded salt formation. So, storage cavern overview. Products that are stored. Primarily, caverns are used to replace spheres, above ground pressurized vessels for storage. So NGLs, ethane, propane, butane, LPGs, crude, light oil like you have in the Strategic Petroleum Reserve, petroleum products, not much here in the United States, but over in Europe, that's a big thing. They do a lot of their strategic storage for their equivalent to their Strategic Petroleum Reserves with actual product instead of crude, and they use caverns for that. Compressed air, We've done hydrogen, as we said. We've done ammonia caverns, which that's also we're going to talk about a little bit later, which is part of the green mix, whether used as a fuel source or as a dense carrier for hydrogen. We've done one of the only ammonia caverns in existence. And then something that's also gaining a lot of interest recently is helium as well. So solution mine salt caverns, we've got a 60, in the top graphic on the right-hand side, that's what a domal salt formation looks like. And those yellow caverns that are outlined there, they're about 300 feet in diameter and can be anywhere from 1,500 to 3,000 feet tall. So you can fit the Empire State Building in that. That's the size of those in the Gulf Coast. Up here in the Northeast, we've got bedded salt formations, and I'll get into that. We're a little limited on the sizes. The Gulf Coast, there's really no limit to how big you can make these. They've been a 60-plus operational year history. There's 2,000-plus caverns worldwide. We've lost count. And let's say there's several in H2 service. And they have been in service, H2 service for the past 50 years as well. Hard rock caverns, once again, there's been a 60-plus year operational history. First caverns in the U.S. Were done out in Linden, New Jersey at the P66 Bayway Refinery. And they've been in service since 1958. There's 200-plus caverns worldwide, and we have demonstrated hard rock cavern performance up to 800 psi. So that becomes important when we start talking about hydrogen, helium, and other kind of pressurized gases, since most of our hard rocks store liquids under pressure. So salt cavern overview. Two types of salt formations that we go into. On the left is a domal salt formation. Now, the domal salt formations are just a giant finger of salt that pushes its way up. This is predominantly in the Gulf Coast, so Texas, Mississippi, Louisiana, Alabama, and then obviously out into the Gulf Coast. Kind of an interesting historical fact about salt domes. The first oil wells down in Texas, although Pennsylvania, we had the first oil well in the country, and I like to remind my friends from Texas about that. The first oil wells in Texas were discovered around the perimeter of the salt domes. That's why they're so well mapped, because as that salt dome, as that finger of salt pushed up, it caused the layers to compress and the oil and the gases to pool around the perimeter. So, Spindletop, Mount Bellevue, those areas where the first oil was discovered in the wells, all around the perimeter of the salt domes. Anyway, and those things are huge. They can be 2-3 miles in diameter and go down 10 or 15,000 feet. So there's really, there's no real practical limitation on how big you make these things, but the biggest one that's been made is about 30 million barrels. Most of them are in the 3 to 5 million barrel range. So that's kind of on average. Now on the right side is what we have up here in the Northeast, and that's a bedded salt formation, and it's just like any other geologic layer. Up here, and I've got a graphic and I'll show it. We've got the Salina F4 formation that goes through the Ohio River Valley, West Virginia, Ohio, Pennsylvania. Good areas to develop down around Parkersburg, midsection around Folensby, and in that area in the center part, and then up around the tip of the Panhandle, and I'll go through that. So here's where the salt deposits are in the U.S. As I said, that area around the Gulf Coast, that shaded area is through Mexico, and that entire region, that is where you find our salt, domal salt formations. All the rest of those are all bedded salt formations. And even, I know there's been a lot of talk about the hydrogen project that Mitsubishi is doing out in Delta, Utah. That's commonly, there's a mistake about that. They say it's a domal salt formation. It's not. It's actually a really cool upturned salt formation that has all the characteristics of domal salt, but it's actually a bed that got moved around during geologic times. So how do we make a salt cavern? Very simple. Drill down into a salt formation, start injecting fresh water in, and for every 10 to 13 barrels of water you inject into a salt formation, you're going to dissolve about 1 barrel of salt. So in the first graphic you see on the left-hand side here, go down to the very bottom of it, you have a sump, and the browns that you see right there are the insolubles that come out of the salt. You don't have many insolubles in the domal salt formation, but in bedded salt, especially through here, you've got anhydrate level layers or insolubles that settle down to the bottom. So your sump design and having adequate space there is very critical. So you start at the very bottom, you inject the fresh water in, dissolve, the brine goes out, and the brine gets disposed of. And then over time, you start pulling the hanging strings up, and then once you get to the very top of the formation, you've created the cavern. The caverns that you see in the Gulf Coast are a lot smoother, and that's because you've got a pretty uniform salt formation all the way through. The reason why you've got jagged edges here on these are because of those anhydrite layers that kind of come in. You can dissolve, some of them will fall down to the bottom, but you're not going to get that really kind of smooth cylindrical shape that you do with your domal salt caverns down on the Gulf Coast. That's why they're jagged. Did I mention there's a blanket layer level up top? The reason why you have that, that's usually a diesel or something else, because you don't want to dissolve too much of your roof and jeopardize the integrity of your caverns. Very critical down here in the Gulf, very critical up here in the Northeast because we've got limited salt layers. I mean, the thickest layer we have up here is about 150, 160 feet. So to maximize that space and have the structural integrity, you've got to be very careful on how you form that salt cavern. So, the Holy Grail, Appalachian salt caverns, nothing's been done yet, and that's because of limited brine disposal in the formations. Down on the Gulf Coast, you can get disposal wells, 1,000 to 1,500 gallons per minute. As everybody knows up here, you're lucky to get a disposal well that can do 100 gallons a minute, and then it's got a limited life. So it's been made, so disposing of it's been very cost prohibitive up here. But those are the areas that you see, the dark red areas. Those are the areas where you have the thickest salt. Like I said, that the Folensby area there in West Virginia, on either side of it, that's about the thickest salt bed we have up here, and that's about 150 to 160 feet thick, very well defined. But like I said, the issue is brine disposal. So, and this is what we've worked on at Lane for the past several years. So, Appalachian Salt Cavern Challenge. 3 resources necessary. You need water. You need and you can get that through surface water, groundwater, the river, or you can also use plant effluent as well. So we're not concerned about the quality of the water. Salt, is limited, but we have locations. Brine disposal, and that is the real key issue here. How do you get rid of it? So Gulf Coast brine, I just put this graphic together. So for a 1 to 10 million barrel cavern, we can typically design it for a flow rate for that fluid of 3,000 gallons per minute, and it takes about 4 months to leach out a 1 million barrel cavern. And it's the cheapest form of bulk storage that you can do. The Marcellus, if we use brine disposal wells up in here, we'd be lucky to get a 200 gallon per minute flow rate, and you're looking at about 45 months to leach out that 1 million barrel cavern. Marcellus bedded brine as a feedstock, either plant effluent or feedstock into what Mountaineer's doing, sending it over to Axial or Westlake's plant now, over in Natrium. They're going to supply, if they ever develop their salt cavern, when they develop their salt caverns, they're going to send that brine over to the river, and it's going to get processed in the chlor-alkali facility. Yes, sir.
What's the challenge with the brine? Are there other compounds of concern in the mix why is it so difficult to get rid of?
Well, it's just the geologic formations are so tight here. You just can't get the flow rate. You don't have the void space into the geology to do it.
The brine that comes back up for surface disposal, what makes it so challenging to get rid of it?
It's not challenging. There's nothing. You don't have any radioactive materials. You don't have. Typically it's really clean kind of sodium chloride. The issue is just the flow rates that you can get to dispose of it. So it really gets to be a disposal well issue. There's nothing technical or environmental about it. It's just the limitation of the really dense geology that we have up here. But,
in the Appalachian region here, what's the depth below the surface to the salt formation?
So I'll take Folensby, that region, because we drilled a core well out there back in 2019. It was about 5,500 feet to the top of the salt. So it's deep bedded salt, really good for high pressure storage. Analogous to what we've done up in Alberta, Fort Saskatchewan area, very similar salt formations up there, very deep. So technically feasible, it can be developed without an issue. So the last one I want to talk about is the Marcellus bedded, and we have a salt crystallizer. So one of the things my partner and I did when we formed the company up is we started working on how do we solve this challenge. We were working with Shale and talking to others. So we worked with a manufacturer to take commercial off-the-shelf equipment, strip it down to everything that wasn't necessary, and we have actually it was just issued in June. So we have a brine management systems for salt cavern development and operations. So we have a patented closed loop system. We can develop caverns anywhere where you do not have brine disposal, or if you've got scarcity of water issues, because we recycle 93% of the water. As it goes through our closed loop process and through the crystallizer, we pull out the sodium chloride, and we only lose about 7% of the water on each pass through that, so we're able to recycle that in there, so we use less and less, so we're not disposing of that water. And then the salt can either be commercialized or we can landfill it. Either way. So we've got a way to develop caverns everywhere up here from West Virginia, Ohio, all the way up through Pennsylvania and New York State, if they ever choose to start allowing us to do that up there as well. They've got some nice caverns up there at Bath and now, but everything's been shut down from an environmental standpoint because of the brine disposal issue. So we're actually having some interesting discussions with some folks up in that area as well. Any questions on salt caverns?
Yes.
Shoot.
So, I know we're talking about Appalachia, but on the Gulf Coast, would the developers be permitted to just take the brine and put it into the Gulf of Mexico?
We've done that before. Yeah, you just run the pipeline out. It's just environmental permit. So that has been done as well because it's brackish water. Yes, sir.
The term salt domes, what's the difference?
I'm sorry?
What's the difference between caverns and salt domes?
Well, the cavern goes into the salt dome. The salt dome is just that geologic formation, and then we leach out that cavern. Yeah, exactly. Yeah, and just to clear up, so we do not work in like depleted reservoirs. All of our caverns are purpose-built, either through the hydraulic process or leaching, or the more fun part, hard rock caverns are a little more exciting because you get to go down, you get to play with explosives, but I'll get into that in the next section here. All right, any other questions? So hard rock caverns. So this is what a hard rock cavern cross-section looks like. And as everybody up here in Appalachia knows, they know what a mine looks like. Instead of pulling the ore out to commercialize it, we're getting rid of the ore and we're commercializing the void space that we create. It's the same exact techniques that you use in any conventional hard rock mine. The only difference is we seal it up, pressure test it, and it's used for pressurized storage. But that's a good cross section. It's exactly what it looks like. Average depth, about the old caverns, about 300 to 400 feet. What we do today, we can go a lot deeper. We got better equipment, larger shafts. So we usually start about 700 feet and go down from there. What do you need? You need competent rock, adequate structural strength, minimal faulting, fracturing, low permeability. So your shales, granite, gneiss, limestone, dolomites, sandstone, chalk. We've done caverns, and caverns have been built in all of those. Favorable and stable groundwater conditions. You want an adequate hydrostatic head, recharge going into those formations because it helps with the containment of the cavern. I'll get that on the next slide. Ample groundwater recharge, either natural or artificial, and then physically and chemically inert. We haven't come across a rock formation yet that had an adverse reaction to a hydrocarbon. So it's a great way to store things. So how do these things work? It's basically a hydrostatic design principle. You've got your external groundwater pressure, and so the depth is critical to the cavern. So every foot of depth that you go down, you've got 0.433 pounds per square inch of containment pressure from the hydrostatic influence of the water. So the deeper you go, the higher pressures that you can store to. In areas where we don't have adequate water recharge, we actually can put in artificial water curtains so that we create that. And that's more prevalent, like we've done the ones in China that we did, they were actually up into a mountainside, so you didn't get that, they were above sea level, so you didn't get that recharge going through, so we had to create an artificial water curtain to get that containment pressure. So there's ways around that. But the leakage mechanism, you actually want water to come in, that's a good thing. And that means that you've got that recharge that you need. Not necessary, but it is good. So legacy hard rock caverns. So everywhere that you see a little box there, that's where we built, have been built in the United States. Then the 2 in China and 5 in Singapore that we did. And you see most of those, they're all in areas where you don't have salt. Salt is definitely the preferred way to store because you can do a lot larger volumes at a more cost-effective rate. And that's why the Gulf Coast exploits that so much because of the domal salt formations and the cheapest storage possible. So global hard rock cavern inventory, there's 83 that have been constructed in the US, 60 are still in LPG service. The ones that are not in service primarily are doing for commercial reasons. The ones in Todd Hunter in Ohio, there was one or two that had pressure issues, and they took all those out of service, but only one or two of them really had an issue. Other than that, it's really a commercial reason why you stop using a cavern. And the life expectancy, the average cavern age right now in operations is over 52 years, 53 years. So we've got a safe 5+ decade operational history. Northern Europe, a lot in Norway, in the Scandinavian countries, France, Germany, and Asia, 24 strategic and 13 commercial. Here's kind of a good cross-section of what a typical hard rock cavern is. The shafts that you see, those are actually dual-purpose shafts. We usually have 2 8-foot shafts, 1 6-foot shaft, and they're converted into pumps, instrumentation afterwards. Basically, it's an underground pressure vessel. It's very easy. You've got, you pressurize the formation, put the liquid in, and pump it out when you need it to come out. And there's really no safer or secure way to store than underground. On the left-hand side here, you see a decline. The majority of all the caverns that we do use shafts to access it, but in areas where you're above ground, the caverns we did in China, for example, that had a decline down into a formation, but it's very costly. Go ahead, sir.
Just want to clarify, make sure I heard you right. So the center shaft there, vertical shaft.
Yes.
6 foot in diameter?
Well, it's not to scale, but this is just kind of an operational graphic. Typically, we have 2 8-foot shafts. The first 8-foot shaft is used to get the muck out. The second 8-foot shaft is used as our kind of our service hoist for men and material. And then we have a 6-foot shaft that we use for ventilation. And then those get, like I said, those get converted afterwards into service for the pumps and for instrumentation. So this is actually a cavern that we constructed, 1.4 million barrels in shale. The red cross section, that's the pillar, that's the rock that remains, and the white areas, those are the galleries that get mined out. In this case, they were roughly about 20 feet by 18 feet by about 30 feet tall. Because of shale, because of the rock formation, we were limited. If you go into limestone or granite, you can get much wider cross sections. One we did in Singapore were 20 meters by 23 meters tall. Just depends on the structural strength. Yes, sir.
What depth do you do in that?
This one was down to 700 feet.
How many?
700. Yeah. All the newer ones that we've constructed as of late tend to be deeper just because it's easier to do. Back in the day, the old timers that did this back in the 60s and 70s, well 50s, 60s and 70s, they brought everything in and out of a 42 or a 48-inch shaft. And if we had more time, I'd show you a video of we've got one from the 1960s on how these things were built. Which if you can imagine all the equipment, everything going out of 42 or 48-inch shaft. So they were different breed back then. So this is kind of a cool project that we're doing right now. It's public. This is going to be 4 caverns and central mining infrastructure, and then we're going to build the caverns, bulkhead them off, put them into service. So we'll have 1 in service, and we'll be mining out 2, 3, and 4. Be an interesting. It's going to be an interesting project. And the nice part about that is you can have multiple products, which is what we're designing it for. So butane, propane, propylene, you'll have the flexibility, green ammonia. You'll have the flexibility to put anything you want in those 4 different caverns. So here's something. So this is our smaller scale, our small plate, our tapas menu, as we like to joke around. We can cost effectively, once you hit about 90,000 barrels, we can cost effectively compete with propane spheres on the surface. So on the bottom there, you see roughly, if you have 90,000 barrels, it's about $425 a barrel. The larger you make it, the cheaper the cost per barrels go down. 150,000 barrels, just kind of pick that number, it's about $330 a barrel. And that's all in. And you still have use of your surface, because just remember, the expression that you have on the surface is just the wellhead and the connections into your processing systems on the surface. So you've got a lot of flexibility here. So as you're thinking about expansion, fractionation, things like that, you've got great shale formations at the depths you need, and we're cost effective. And you can use the land as well. So you can put these anywhere. One of the things that we have right now that's patent pending, we call this our hydrogen silo. So we're using this for smaller scale stores of hydrogen. It's basically, we're making it, this is the same shaft that we use to go down to mine out a hard rock cavern, except we don't cut the bottom off and mine it out. We just leave the bottom of it in there, and we can pressure that up, and probably 400, 500 psi. And once again, there's no safer way to store any kind of pressurized gas than underground, where all that energy is contained well below the surface. Any questions? I'm sorry?
Especially if it ignites.
Things, yes, exactly right. So that's where, unlike having spheres on the surface and shell and tubes, you don't have to have that same kind of safety barrier. You don't have the fire protection. You don't have to have the blast radiuses that you're concerned about for any of these things. Everything is contained underneath, and you just have the pipes on the surface and the wellhead. So current trends. NGLs, LPGs, we're still kind of kicking the tires here in Appalachia. It's going to happen. There will be a storage facility built. COVID kind of, got everything off track for a little while, but we fully anticipate as things kind of kick back in. Let's face it, plastics aren't going anywhere, and neither is our industry. So this is going to be happening. Natural gas, renewed interest, especially after the winter we had down in Texas. A lot of interest now in strategic gas storage, down in the Gulf Coast region. We've fielded several inquiries and talking to a few folks about that right now. Hydrogen, this is the topic of the day. This is the cool stuff. It's proven. There are several large projects that are in development. Mitsubishi's got a really nice project out in Delta, Utah. They're also doing some work up here in CAES and other areas around the country. So they're really interesting, as hydrogen as a fuel source into power generation. And with that, you're going to need hydrogen hubs. Actually, up in North Dakota as well, there's a nice little press release about Bakken Energy about putting a hydrogen hub up in North Dakota as well. Helium, not just for kids' birthday parties and balloons, but as an industrial gas. That can also, there's a renewed interest in this as well. So we see that, and helium, I didn't realize this until you really start digging into it, but it's used as an industrial cooling gas for like MRI machines. So every time you go in for an MRI, those magnets are super cooled with helium. Interesting little tidbit there. Green ammonia. There's a lot of talk about this as a carrier for the hydrogen. There's several ships that are being built right now as both ammonia carriers and also being able to be fueled by ammonia. So NH3, it's a nice dense hydrogen carrier. We're going to see a lot more in that. Also, once again, very easy to store in hard rock caverns. You can't do it in salt caverns because they're brine compensated, but it can be easily put in hard rock caverns, and that hard rock is prevalent throughout the entire world. So we're pretty excited about that as going forward. I think we're going to see some really serious traction there in green ammonia. Compressed air energy storage. There's two in existence. The one here in the United States is in McIntosh, Alabama, built in 1991. But once again, there's some really interesting things going on with CAES, but more on the advanced CAES side, and I've got a slide on that. So where's the U.S. current interest in caverns right now? Believe it or not, New Jersey, we've got NGLs, ammonia, and hydrogen being looked at and developed there. In our region, we've got NGLs and hydrogen. Mid-continent, Chicago, that area, NGLs, hydrogen. CAES, compressed air energy storage, hydrogen on the West Coast. The CAES in H2 in Utah, that's the project that Mitsubishi's working on. And then down the Gulf Coast, we've got everything down there. We've got NGLs, natural gas, helium, and hydrogen. So, hydrogen storage caverns, why now? Green energy trends are driving the process. Europe is probably 2 or 3 years away from us right now. They've just got out ahead of that. Their energy mix, their cost profile, a lot different than here in the United States. But they're making great strides in pipeline conversions and storage and uses for, whether it be power generation, whether that be transport sector. They're making some great progress there. There's several new developments throughout Europe. And why not for hydrogen storage caverns? Very large volumes, very cost effective. There are 6 caverns in the world. We have 3 in the UK, and they've been in operation since the late 60s, early 70s in Teesside, England. And then there are 3 caverns here in the US, all down in the Gulf Coast. Like I said, we did the last one for Air Liquide back in 2015. Design and operation, very similar to natural gas caverns. They're a direct analog. It's just a compressed gas. The only difference is, as everybody knows, is how you treat the casings. You have to have the special weld procedures because of the hydrogen molecule. Otherwise, we've been using hydrogen for industrial applications for the past 100 years. There is no great mystery about this. It just has a resurgence now, to reduce emissions. We get questions. can you convert existing caverns into hydrogen service? No. You can, but it's not the best application. The well casings are not designed for it. So we can either put a liner and a packer in the existing casing, but you're gonna throttle down your flow rates through that, or you can plug and abandon, cap that existing well and just do a re-entry well that's purposely designed for hydrogen. So can we take an old one? Yes, we can convert it, but you do have some limitations when we do that. The best thing to do would be either a new cavern or a new entry well into the cavern. So here's some other green energy trends where hydrogen is going to kind of play a role as well. So compressed air energy storage. Everybody familiar with this? Have they heard about it? It's analogous to a pump hydro storage, but instead of putting water up into a dam, you're compressing air down into a cavern during off-peak hours. And then during peak hours, you're releasing that air. It's going through the turbine, and then you increase the electrical output of that turbine that uses natural gas alone by about 30 or 40%. But it's costly, caverns are expensive, and as we all know, natural gas, we're the leader here, it's very cheap, and that's the reason why nothing's been done in 30 years on that. But I do think when we start talking about the hydrogen and using hydrogen along with the mix in these turbines, you are going to start to see compressed air energy storage projects probably being mixed in with a hydrogen storage project as well to do joint hydrogen turbines. So we're at a pretty cool little spot here. That's why I put it in there, so something to look about as far as the trend. This one's interesting as well, and once again, there'll be a part that I think hydrogen's going to play with this. There's a company called Hydrostor that's doing advanced compressed air energy storage. And what's interesting about this is typical CAES projects use salt domes. The advanced case is going to use hard rock caverns. And the difference between this and the others is they've got a pond, a freshwater pond on the surface. So as you charge up the cavern and take it up to about 800 PSI, you're going to displace the water up into the pond. And then when you're ready to release that air into the turbine, well, that water comes down, and what's interesting about that is you don't get a decrease in the pressure, so you get a constant pressure and mass flow rate out of that cavern going into the turbine. So that's something to keep an eye on as well. You're going to be hearing more about this in the future, and then once again, you're going to couple that with a hydrogen-powered turbine, and this is going to be in the mix for renewable energy. So cavern cost and development. Basically, I'll just go into for a salt cavern, a month or two for geologic pre-feasibility, another 3 to 4 for core drilling and salt core testing, another 3 to 4 for front-end engineering design, permitting, 6 to 12 depending on the jurisdiction. So we're looking at 43 to 70 months on a development for a 1 million barrel cavern, just depending on the jurisdiction and the flow rates with the crystallizer and everything else that we go into. Hard rock caverns, a lot faster, 1 to 2 months for the pre-feasibility, 3 to 4 again for the core drilling, 3 to 4 for the design, 2 to 3 months to permit. Permitting a hard rock cavern is easy. It's just a simple well permit, and issued by the oil and gas in whatever jurisdiction you're in. So permitting is very, very simple to do. And then construction, 27 to 30 months. So from start to finish, you're looking at about 3 to 4.5 years to put 1 million barrel of cavern into service. CapEx, what's it cost? Hard rock, and the deeper you go, the more expensive you get. So, hard rock caverns down 2,000 feet, max pressure 800 PSI. You're looking at, $133 a barrel for 1 million barrels. And then here's the important thing to remember when you're developing a hard rock cavern is your first barrel of storage is your most expensive. So your first barrel is going to cost you about $30 million, $40 million. And then it's just the incremental mining cost thereafter. So the larger you make it, the cheaper per barrel cost it is. Down at shallower depths for your LPGs at 750 feet, it's $109 a barrel for 1 million barrels and about $180 a barrel for that, 180 million for the 2 million barrel cavern. Sorry about that. All right, Gulf Coast salt, this is the cheapest storage you've got. Average depth down there, 4,000 foot for the cavern, 1 million barrels, you're looking at $80 million start to finish. Now, it's important to note the incremental cost thereafter, because you've made the investment in the infrastructure, the leaching facilities, the brine disposal wells, the water wells, all that, your incremental cost to develop that next 1 million barrels is only about $10 a barrel. So once you make that investment, and that's why the Gulf Coast is so prevalent, because it's just so cheap to work down there. All right, up here in Appalachian salt, so depth 5,000 feet down, max pressure 3,400 PSI. I put working mass in there for hydrogen. It's important when you're looking at, for a turbine feedstock. But it's about $82 million for your first million barrels. 2 million barrels, incrementing once again, it goes down because you've already made that investment. Cavern development stages. I'm sorry, go ahead.
So, you briefly mentioned the pumped storage of water.
Yes.
Can you talk a little bit about the advantages and disadvantages of water versus compressed air?
Well, okay, for the water that's used in the compressed air energy storage.
Like if you were to do pumped storage with a dam and water, how does that compare to?
Well, I'd have mine done and operational before the environmentalists gave you the permit to do your dam. That's another reason why there haven't been a lot of those built, because of the environmental permitting, as everybody knows, especially when it comes to damming.
Compressors are 1/10 the efficiency of a pump as well.
Yeah.
There's the big one.
True.
There's the big water one in West Virginia that's not too far from here.
Yeah.
Bath County is the water one.
Yeah, no, they're great. They're efficient. But listen, the compressed air energy storage is the reason why there's only 2 built in the world. They're not that efficient. But subsidies, policy changes, things like that, it's this is coming back around again. But pumped hydro storage, it's great. We should be doing more of it because it's a good renewable. Any questions on cost? So if you're interested in developing a cavern, about $25,000 to $50,000 for the desktop geologic study. After that, we've got pre-feasibility, which is getting a hole in the ground. Hard rock caverns are about $750,000 per hole. Salt caverns, because of the depth and the size of the core, we need a 4-inch core. You're looking at about $2 to $4 million, depending on the depth up here. Here it's closer to the $4 million because we have to go down very deep. Definitive feasibility for a hard rock cavern, you need to do additional cores. You need to core out the entire geology around the perimeter so you can accurately map it, so you need more than one core. In a salt cavern, you only need that one. You take that core, you test it, and you can develop your leaching program no matter what, so you don't have to do anything further. And then your FEL3, your feed, once we do all that design, you're looking at spending about $750,000 to another $1.5 million for us to put together a full design for you to get to construction and go forward. So key takeaways that I want to talk about. Hydrogen is forecast to become $130 to $170 billion U.S. industry by 2050. So this is all something that we need to pay attention to, and it's going to exist with our industry hand in hand. Natural gas, hydrogen, they're going to coexist for the foreseeable future. Biden's infrastructure plan allocated $73 billion for clean energy transition, and in that there's $10 billion in there for hydrogen, pipeline, research, storage. Several other interesting things in that. I thought one of the most, if you ever get a chance to read it, it's a good thing if you try to fall asleep or something like that, pick up the infrastructure plan and start reading through there. You'll be fine. You'll be asleep in no time. But in there's actually a shot at electric vehicles, where now they've got to take the full account of the carbon used in the entire manufacturing process, mining process, and give the true carbon footprint of electric vehicle. Why I mention that, I think that's very important because hydrogen is a fuel source into the internal combustion engine. They talk a lot about hydrogen in the fuel cells, generating electricity using the cars, but they're not talking about using hydrogen directly into the combustion engine, which has been able to done for 100 years. So I think whoever put that in there, the intent was to start focusing on being able to use hydrogen as a refuel, as a replacement for gasoline or supplement to gasoline in certain areas where they're fleet vehicles or whatever. So I think there's going to be some movement in towards using hydrogen as the direct fuel source into internal combustion engines. So I thought that was pretty interesting. DOE, Department of Energy, has got their H2 Earth shot that the Secretary of Energy came out, $1 kilogram by 2030. They're putting the money, and they've got this money into the infrastructure plan for that development. So hydrogen can be stored in salt caverns and hard rock caverns. It's important to note, though, we've never done a hydrogen hard rock cavern. Technically, it's feasible. We've done caverns to 800 PSI, so we can store it at those kind of pressures, and we can store it at lower pressures too. If we wanted to put a hydrogen cavern at 1,000 feet, we could store up to 380 PSI or 400 PSI. So it is possible. It's not been done yet. So that's an important caveat. And like I said, in the salt caverns, they've been around for 60 plus years, and 50 in operational service for hydrogen. Green ammonia, definitely pay attention to it. It's going to be part of the energy mix going forward. transport, marine transport, and as a carrier, and maybe even a fuel source into turbines for power generation. Caverns take a long time, long gestation period. So if you want to do one, let's start early. Any questions? All right.
Have there been any hydrogen storage, and I realize you guys do caverns,
Yes.
but has there been any hydrogen storage either successful or attempted yet in converted reservoirs?
You know, they've talked about it. I think they've studied it, but the problem is since hydrogen is a purity product, the heel that you have to leave behind would be very costly. So I don't think with something like hydrogen and helium and others, you want that into a cavern that you've got defined void space area, so you can get it in, you can get it out with limited heel. But putting it down into a reservoir, you know, I don't know what kind of percentage you get back out of that, but it is being studied.
Yeah, I was curious because it would seem to me to not be the best of ideas.
No. No, there was.
Well, it's a smaller molecule, and it's going to be able to find its way further than the natural gas that was in the reservoir to begin with. So it's going to be harder to get out once you put it in.
Exactly, and I think that's, you know, they've studied it, they've looked at it, but I don't think anything will happen with that.
And then actually I have a second one.
Oh, shoot, go ahead.
So green ammonia.
Yes.
You want to explain? I think I know what you mean by green ammonia. You want to explain?
It's just made through renewable energy sources.
Right.
So that's it. I mean, it's.
So it's not made by the natural gas that we know.
You know, I got to be honest with you. The talk about the different colors and things like that and the definitions, basically it's, you know, low carbon intensity ammonia. So whether they use a carbon capture system, you know, they take the methane, you know, convert it, you know, reform it, convert it to ammonia, but they capture it. They use green energy. They use, you know, green electricity to do that. It's not really clearly defined on any of these color ranges yet. I mean, you've got blue, gray, you know, black, you know, magenta, whatever. But yeah, it's, you know, low carbon intensity. I think that's going to be probably the measure going forward is how much carbon did it take to do it, you know, and how much to release, you know, during the process, and that'll determine. I think hopefully we're going to get away from the color scheme and get more into the carbon intensity during the manufacturing process.
What test medium do you use for the pressure test in the cavern, and what are some of the general requirements of the pressure test?
So if we're putting the cavern into service initially, we'll pressure up with air, and then we'll purge it with nitrogen. Just because it's, you know, be an ungodly amount of nitrogen to do that with. If we've gone into an existing if we're going back to an existing cavern and repressure testing it, then it'll be 100% nitrogen, just inert gas, and then gets flared out.
Thank
Yep.
you.
Yes, sir.
So if, as an example, if Shell needed NGL storage in the Fallen Speed area, and they started today, as soon as it could be operational, it would be a little over 4 years?
Yes, for your first initial, and we've done this. We've actually looked at a site in Follansbee. I love the salt there. It's probably one of the best places in the region to do that, just because it's the thickest salt beds that we have. You know, you're looking at a year to get the crystallization equipment, another year to you know, 6 months to get that up and operational, and then we could leach out about 750,000 barrels a year at a 500 gallon per minute flow rate. Go ahead.
So the follow-up is, what about the practicality of something under Lake Erie?
Yeah,
Salt, right?
there's bedded salt up in that region. Yes.
Is it thicker though than the 160 feet?
You know, I don't know. We've never done any work up there. We've done work around Detroit, Sarnia, but we've not done any work under Lake Erie at all. So I'm not familiar with the salt beds and their thickness up there. But it is in the UK and in North Sea. There have been salt caverns developed under the sea. We've done a lot of work down in Louisiana. My partner worked on the loop caverns, which are, you know, underneath the bayous there. So you can leach out. It's not something that's been, you know, not very common, but it has been done. Any other questions? All right.
So you're suggesting that this study that track all of the carbon in these energy projects are going to prove that solar and wind will not compete with hydrogen when you consider the entire beginning and end of all this carbon that's involved in, say, mining for rare earth, et cetera.
Well, I'm not saying that. I'm saying that that doing a carbon intensity is going to help level the playing field wherever that falls. So when you start taking a look at the entire process all the way through, it's going to level set a lot of these things, and we can have an honest discussion about, what makes the most sense.
We can have an honest discussion amongst ourselves, but the general public may never get that information.
That is a problem. Anything else?
38 out of the 48 states, right? The emissions profile for power generation for the grid is dirtier than the propane emissions. And propane is this molecule you guys are all familiar with. And that's my industry, but we can't get that story out.
No, and it needs to be told. It does, because the general public is not getting, there's a lot of interesting books out there. Michael Schellenberger that wrote Apocalypse Never, really interesting read that kind of breaks everything down. And there's information out there. We just, it's just not widely disseminated, unfortunately. But I think we start taking a look at more, and if they do start taking a look at more from the carbon intensity of the entire manufacturing process and usage profile, that'll be good, because we'll start to have a real honest conversation about really where things fall. So anyway, thank you very much. Appreciate it, and thanks for the invite.